Hi everyone, my name is Darwin. I am a PhD student from Adelaide Uni, and today I'll be talking about the In-situ Rb dating of Precambrian sediments. I just want to thank all the partners who've supported me throughout my PhD. And to start off with, I just wanted to take a step back and talk about something that's always intrigued me. Um, I've always been interested in understanding how life on our planet has evolved through time, and this question has formed an overarching theme throughout my PhD. Oxygen is obviously important and integral to the development of life, and this model from Lyons et al. Uh, shows how we think atmospheric oxygen levels has changed on our planet. The faded red curve shows the classic two-step view of how we used to think atmospheric oxygen um, has evolved, with the blue curve showing more recent and emergent models of the same question. The big blue bars through the Proterozoic shows how little we know about this era, and evidence for all these interpretations are anchored in the geochemistry of sedimentary rocks, such as redox-sensitive trace metals and shales, rare earths and carbonates, as well as isotopes in different marine sediments. Well, all of these archives are only useful if we could chronologically constrain them, and Precambrian sediments are notoriously difficult to date, as there's a lack of a diverse faunal record, and hydrothermal or metamorphic orogenites can also be challenging to assess. And here we demonstrate a new approach that has the potential to rapidly and accurately evaluate depositional and alteration histories of Precambrian sediments, where a reactive gas, such as nitrogen oxide, can be introduced into a reaction cell within a laser ablation mass spectrometer and allows for the separation of a parent and daughter isotopes with the same mass, such as A7 strontium from A7 rubidium. And unlike the traditional method of whole rock digestion, in-situ analyses can maintain textural context of samples as well as simultaneously collect elemental and isotopic data. And for my first case study, I looked at samples from the McArthur Basin in northern Australia. This Proterozoic sedimentary system records a billion years of Earth history and hosts the world's oldest petroleum pipe. I've targeted two wells, Yearpunga 5 and 6, with the Yearpunga 5 drill core intersecting a hydrothermally altered dike from the Derim Derim sweep at around 210 meters. This dolerite sample was analyzed alongside a shale sample from the Geological Formation, which is around 80 meters away from the intrusion, as well as shale sample from the wooden duct member around 300 meters away from the intrusion. High-logger data shows the high abundance of high temperature minerals such as chlorite and dicite within Yearpunga 5, likely indicating a thermal overprint caused by the intrusion. On the other hand, drill hole Yearpunga 6 did not intersect the dolerite sweep, and high-logger data from this well shows an absence of the high temperature minerals. Shale sample UR6269 was taken from the GIB member within the minor roof formation. And rubidium strontium age obtained from the dolerite overlaps with crystallization ages of the Derim Derim intrusion obtained elsewhere in the McArthur Basin at around 1300 MA. Now, what's interesting is that this sample yielded an extremely radiogenic inertial ratio of 0.73, which is seen in the inset of diagram 8. Ages and initial strontium ratios from the Geological Formation and the wooden duct member also overlap with that of the Derim Derim Dolerite. And these ages are a lot younger than expected depositional age, and the initial ratios are also a lot higher than what you expect of seawater at the time of deposition. On the other hand, the GIB member from the intrusion-absent Yearpunga 6 yielded an age consistent with what we thought would be expected age of deposition, and in its initial A7, A6 strontium ratio also overlaps with coeval seawater at around 1.5 Ga. As such, we suggest that the GIB member sample is the only one that recorded the early depositional history for the Rupert group. Rare earth values from the Gibb member was then used as a relative comparison for the remaining sample set, as the Gibb member was presumed to be the best preserved shale, and all the remaining samples show a light rare earth depletion pattern when normalized with the Gibb member. As such, we can confidently say that the rubidium-strontium isotopic system, age, and chemistry of the European 5 shales seems to have been reset by the Derim Derim intrusion. And in my second case study, I look at the Proterozoic South Nicholson Basin, also deposited in Northern Australia. And this basin holds a number of base metal deposits. My study targeted the Doomadgee Formation from well Amoco DDH A3-4. And on the left-hand strat column, we have uranium-lead tuff ages, constraining the unit to be around 1613 Ma. And a recent rhenium-osmium black shale age seems to concur with this depositional age, although this rhenium-osmium has a very large error of around 16 million years, which is troublesome because it overlaps with the underlying formations. And the first sample I analyzed from the Doomadgee Formation is this glauconite siltstone, showing visible sedimentary structures like bedding and swamp deformation structures. And glauconite commonly forms in marine sediments under low oxygen water columns. A sample yielded an age overlapping with the tuff from the same formation at around 1600 Ma. And in addition, the strontium initial ratios are overlapping with coeval seawater at 1.68. Compared to rhenium osmium, this analysis was a lot quicker as well as cheaper. Rhenium osmium will cost you a couple $1,000, whereas this was a couple $100 for a day's worth of analyses. And this type of analysis was also not destructive, and in addition, yielding half the error of the rhenium osmium age. Second sample analyzed were these green phyllosilicate aggregates, cross-cut by a veinlet in the middle of the sample, and has pyrite visibly growing with these phases. And the age roughly overlaps with the uranium-lead fluid-derived xenotime age is found within the screen. And the initial ratio of the sample is extremely radiogenic and not reflective of seawater at proposed time of deposition. And it's interesting to see that these previous two samples are very close to each other. And this might indicate that fluid resetting might not have as big of an impact or an aureole when compared to an intrusion like previously discussed in the McArthur Basin case study. And my last case study is from the Tapley Hill Formation in the Adelaide Super Basin, which Tapley Hill is an interglacial formation found around the big parts of South Australia. And rhenium osmium age constrained this formation to about 643 Ma, although this age combined two different samples from two different localities. Calcareous shale from the Tapley Hill Formation in Arquilula was analyzed and yielded an age overlapping with the rhenium osmium. This result can be improved by perhaps anchoring the isochron to an initial ratio that can be easily obtained from the interbed carbonates. Nevertheless, the pristine initial ratio displayed here indicates that the Arquilula sample region may not have been affected as much from the Paralana fault, and therefore this region can be used for further paleoenvironment studies of the interglacial Earth during the Neoproterozoic. And thank you so much for listening.